Hi everyone, welcome to the International Medical Scientists webinar. My name is Donna Litch and I'm from the International Student Recruitment at the University of Tasmania. So today we are meeting across La Trowina, Tasmania, Aboriginal land, sea and waterways online. I acknowledge with deep respect the traditional owners of this land, the Palawa people. And welcome today for everyone from all across the globe. With the COVID-19 pandemic, it has highlighted the need for more scientists to conduct more research, and the demand for job opportunities in this space is very high. Hence, our laboratory medicine courses have been very popular more than ever. So today, we're very lucky to have Dr. Jeff Beckett to talk about these courses. So Dr. Jeff Beckett is a lecturer in the laboratory medicine at the School of Health Science at the University of Tasmania, and he teaches the Bachelor of Laboratory Medicine and the Bachelor of Health Sciences degree programs. So today, before I hand over to Dr. Jeff Beckett's presentation, I'll remind everyone that if you have any questions, feel free to type into the chat box. And at the end of Dr. Beckett's presentation, we will attempt to answer all of those questions. So over to you, Dr. Jeff Beckett.
Thank you, Donna. Thank you for that introduction. So I just want to say welcome to everyone, and I'm glad that you can join us today for this presentation. As you heard, my name is Jeff Beckett, and I'm a medical laboratory scientist. I teach both into the Bachelor of Laboratory Medicine, but also the Masters of Laboratory Medicine programs. I also assist in the coordination of the Masters course itself, and also in our professional placement program. In addition, I also undertake research here in our laboratories in the School of Health Sciences. Now, I'm going to talk today about a topic that obviously we have all been affected by enormously over the past 18 months. I'm going to talk about COVID-19. Now, much of the current interest is, of course, about the rollout of the vaccine or the different vaccines that have been developed over the past 18 months. But I'm going to talk about COVID-19 within the context of the role of the medical laboratory scientists that we train here at the University of Tasmania in the School of Health Sciences. So I could have the next slide. Thank you. So just before I start, I think it's important to note that throughout this presentation, I will mostly be talking about our students and the professional career pathway that they traditionally follow, and that is, working into diagnostic pathology labs. However, our graduates also have a definite pathway into medical research, if that is what they're interested in. So they can follow a traditional honours or PhD programs that we have established within our school. So it's a very versatile degree to undertake, gives our students great options upon completion. They can work or can choose to seek work immediately in a diagnostic pathology lab environment, or they can choose to pursue further study and to enter into the research world. Our specialty, though, is of course in training students to become great medical laboratory scientists and to enable them to work in diagnostic pathologies. And we've sent students all around the world once they've graduated. Now, our course is accredited by the Australian Institute of Medical and Clinical Scientists, or AIMS for short. Now, the most sought after medical scientists are those that have an accreditation as a medical scientist. Now, this accreditation indicates that the graduate is highly trained in skills that are specifically required for the industry and is job ready, and that's really important. Now, the Australian Institute of Medical Sciences has accredited both of our courses, both the Bachelor of Laboratory Medicine and the Masters of Laboratory Medicine degrees, and our graduates are therefore eligible for direct entry into the Australian Institute of Medical Sciences. Other than that, our program is also noted for the great quality of graduates that it produces. We regularly receive glowing feedback from our laboratory partners when our students have gone on placement in the final year of their study. So the working prospects are great for our students due to this established quality of our training and the accreditation that our course holds. Now, if you look at the photograph on the screen now, you can see one of our final year students, Deepa. She is actually on placement as we speak in a laboratory in southern Tasmania. And she's being shown the ropes by one of our recent graduates, Veena, who's holding the blood samples and is currently working in that laboratory since she's graduated. So anyway, let's talk about the COVID-19 pandemic and how scientists like those that are on screen fit in when they graduate. So let's first discuss COVID-19 and coronaviruses and some of the terms that you would have heard in the past. As you all know, COVID-19 is a respiratory disease, and the name COVID-19 is the name of the disease rather than the virus, of course. COVID-19 is an acronym and which in its full form reads as Coronavirus Disease of 2019. So it really lays out for us what exactly this disease is and where it's come from. COVID-19, as I said, is the disease, and it's caused by a virus that is named SARS-CoV-2. Now, this, of course, is also an acronym. We love acronyms in science. This acronym stands for Severe Acute Respiratory Syndrome Coronavirus 2. So, number two, what does that mean? This virus was given this name because it was genetically related to the coronavirus that was responsible for the original SARS outbreak in 2003. So while they're related, they are different, as we'll see, and they have actually had quite different impacts, which will be quite clear when we look at the stats in just a moment. So what is a coronavirus anyway? It's a virus that has a characteristic appearance when we look at it microscopically. It's a circular or spherical particle, but it has these prominent crown-like thorns, if you like, all over its surface, which gives it a crown appearance. And the word corona is derived from the Latin word for crown. So hence coronavirus is the word that's been termed for this family of viruses. And it's a fairly big family. It's a collection of perhaps hundreds of different viruses. There are probably only 7 or so different types of coronaviruses that actually cause human diseases. And they mostly cause a mild to moderate respiratory illness. Okay, for example, the common cold is caused by a coronavirus. We know a number of these viruses affect animals only, but we also know that there is the potential that they can occasionally jump from animal to human. We know at this stage that there have been 3 coronaviruses that have been able to cause fatal disease in humans. So as I mentioned before, the original SARS virus, SARS-CoV-1, was responsible for the epidemic of 2003. It's now considered to be eradicated in humans. In 2012, another virus emerged and was known as the Middle East Respiratory Syndrome Coronavirus, and that occurred in 2012. We're still not entirely sure whether that virus has been eradicated. As you can see on the graphic on screen down in the left-hand corner, although these previous viruses were able to cause severe disease and death, neither were able to spread to the extent of the current SARS virus that we're dealing with. So this graphic down in that left-hand corner is from way back in April. So it's actually from when we were still really in the early days of the current pandemic, but you can see that the current virus had at that point already vastly outstripped the effects of these previous outbreaks. So there was already over 80,000 people that had died compared to about 1,600 from the 2 viruses previously. So in terms of symptoms, we know that the most common symptoms are of a cold-like infection. However, there are a variety of possible other effects that can be seen. As we know, there's often about a week or so period from when a person becomes infected with this virus to when they become symptomatic. And that's a real problem for us in terms of trying to control the disease, because if you don't think you're sick, why would you get tested? Now, we know that's probably about a third of people won't even develop symptoms. So again, that's a real difficulty for us in trying to control this disease. Over time, we know that symptoms such as fever and fatigue and that characteristic dry cough will develop in the majority of people. Some people will develop a severe illness, which includes a shortness of breath and maybe developing into pneumonia. Some people will become critical, and sadly, some people will actually die. Now, among those who develop symptoms, probably about 80% of people will actually recover from the disease without requiring hospitalisation at the time. About 13% or so will become seriously ill and will require intervention like oxygen, and about 6% will become critically ill and need intensive care. Next slide, thanks, Donna. So what are we actually dealing with here in terms of a virus? What you can see on your screen to the right is the coronavirus and its mechanism in which it invades human cells. We're just going to focus, I guess, on the anatomy of the coronavirus just for a moment before we look at the mechanism of entry and the way it goes about replicating. Remember, we said that these viruses are named because they look like a crown with thorny projections. So what we can actually see here at point 1 is the coronavirus particle. And it's shown here to have a host of spike proteins across its exterior surface. These spike proteins play a really crucial role in the way in which the virus gains entry into the cell, as we'll see in a moment. If you look at the structure of the virus at this point, you can see it's a spherical particle, and it has a membrane structure. So what you can see on screen indicated by M protein is part of this membrane, and the membrane essentially encapsulates the viral genetic material. The genetic material in coronaviruses is RNA. Now, as you probably know, in humans, our genetic information is stored as DNA in cells. And when we want to make new molecules, such as proteins, we take a copy of that information and we take it in the form of an RNA molecule. And we use it essentially as a short-term recipe, if you like, for the synthesis of our new molecules. Now, this is the process in which the virus uses to replicate itself within human cells, as we'll see. Now, the spike proteins are important for entry into the cell, as I said. They bind to a protein on the human cells known as ACE2. And this stands for angiotensin converting enzyme 2. And this binding acts a bit like a lock and key. It allows entry of the virus into the cell. Now, what is ACE2 doing there? It's actually present on many tissues, particularly through the lungs, in the heart, in the blood vessels, as well as the kidneys and liver, all organs that are affected considerably during coronavirus infections. Now, ACE2 is there to essentially help control other proteins, which, if they're left unchecked, can lead to increased blood pressure, increased inflammation, and eventually damaged tissues. This is really important in COVID-19 because when we have viruses that are bound to that receptor, the ACE2 receptor, can't do its normal job. And so this leads to that inflammation, and it leads to death and damage of cells within these tissues, such as the airways. And this is one of the reasons why, or for the respiratory damage that we see in COVID-19. Now, the virus is a simple kind of thing. All it really wants to do is get access into that cell. So it binds to ACE2 as its way in. Okay, once it gets into the cell, it unpacks itself and it unpacks its genetic information, as you can see on the screen. So the little squiggly line in the center of our virus is the RNA. And so that's the instructions for making more viruses. And it basically uses the human cells machinery to make more viral particles using those instructions. Once they're all assembled, we have a new virus particle, and it can be packaged up and it can leave the cell. It can leave the cell and then infect other cells in the close surroundings, or it can be transmitted through coughing and sneezing and the ways we've learned about to infect other hosts. Now, on the left, you can see a beautiful photo of virus particles here emerging from a host cell. So the orange balls are new viral particles that have just been produced, and the grey background is a host cell, so a human cell. It's been cultured in a lab, but it's a great representation of what's occurring in a real infection. Next slide, thanks, Donna. Now, one of the reasons why Australia was able to control the virus as well as it has is because of its commitment to diagnostic testing. And this is where medical scientists come in and do an amazing job. Through the peak early phase of the pandemic, Australia had the highest rate of diagnostic testing in the world. What this meant was we were able to identify outbreaks and their sources really quickly and put into place controls to help prevent further spread. And it was people like our graduates working in labs which contributed to this process and enable us to get this great control. Now, in terms of testing, or now in terms of the diagnostic testing, Australian labs don't isolate the virus itself, but they do use a test which detects its presence. And this test is referred to as nucleic acid testing. The test specifically is referred to as a reverse transcription PCR test. And what it does is it detects RNA, essentially. So we can use this as the key method, really, of detecting the virus during that acute illness phase. So as soon as you become infected and the virus particles start being replicated, we can start to detect it. Okay, and this is our best way of doing it. These tests are highly specific. They've been designed to only detect SARS-CoV-2. And what they're doing, as I said, is detecting certain parts of that genetic information that is found in the virus RNA that we saw earlier. So typically our tests will be looking to detect 2 or more targets within that genetic information, and it may be genes that code for part of that membrane that we saw. It may be genes that code for the spike proteins, or it may be some of the different enzymes that the virus uses. All these positive results are confirmed generally with a second test, and it's essentially the same test, but it looks to detect other different targets just to ensure that it really is the virus that we think we're detecting. The average turnaround for this type of work is probably 4 to 6 hours. So from the time the swab is taken to the time that that result is reported, it may be 8 to 10 hours, for example. Now here in Tasmania, we have quite a small population. But our laboratories over the past 12 months or so have performed over 170,000 COVID-19 tests. So they've been doing some great work. In Australia, again, population-wise, we're not a huge country, but we've conducted over 14 million tests to date. Globally, things have got out of control in some countries, of course, and so there's been hundreds of millions of tests performed. In the US alone, they've tested over 370 million people. So that testing burden, although there's the collection from your nurses and other people that are collecting the swabs, but the actual testing burden is borne by the medical scientists. Now, outside of nucleic acid testing, there is other specific COVID-19 tests that may be conducted. There are serological tests which rely on the detection of antibodies that our body produces against the virus. It's not that useful really in detecting the infection early on, like the method I just talked about, because it often will take us about 14 days to make antibodies. But it can be quite good in detecting people that have already had the infection or seeing whether their vaccination has been effective. Another important aspect is the area of genomics. And although this is not a huge focus for diagnostic pathology laboratories, it is an important part of the fight against the disease. Now, genomics involves the tracking of new variants that are emerging. And I'm sure you've all heard about the UK and the South African variants. And these are essentially new versions of the virus that have mutations, which allow them to behave a little bit differently. And generally it means that they can simply spread faster and be more efficient in infecting people. Now, as I said, it's not a great focus of diagnostic labs, but all positive tests in Tasmania are actually sequenced so that we can confirm for sure what virus we have and what strain we've detected. Now that's the diagnosis side of things, but there is much work to be done outside of the diagnosis for our medical scientists. So our COVID complications, as we know, aren't just respiratory. There are all sorts of hematological and chemistry disturbances that are common. So the pathology laboratory will be busy in helping to monitor the disease in other areas. So from a hematological point of view, many critical patients will be at risk of thrombosis, which is abnormal blood clotting, and the hematology department will lead this investigation. From a chemistry point of view, kidney and liver function problems are common as well as a number of other abnormalities. And so the clinical chemistry department will be active in doing extra work outside of the diagnosis. And this is just within that acute and near acute disease phase. What we know is that the patients that survive a moderate to severe disease are probably going to have long-term symptoms that we need to manage and will require a post-COVID-19 evaluation and care. And again, the medical scientists will be there contributing to this ongoing care through testing, which will enable us to monitor therapy and so forth. Next slide, thanks, Donna. So with so much work in the background, our graduates have a great platform to forge a career that can have a very meaningful impact on the community. How do they get to that point? They undertake training, which teaches them all of the core knowledge and the skills to enable them to contribute to this body of work. So we teach them across the major professional subdisciplines of clinical biochemistry, hematology, transfusion science, histopathology, and microbiology. Within this environment, we're teaching them all about the methodological aspects of the test procedures that they'll use in real-world laboratories, but also the clinical relevance of these tests. So in clinical chemistry, our students will be trained to perform tests for liver function, for example, for kidney function, but outside of that, things like diabetes diagnosis and tests for all sorts of other assessments. Within hematology, our focus is on hemostasis and hematopoiesis, and also blood transfusion science. So here we're looking at learning about the diagnosis, treatment, and prevention of blood diseases like leukemia, and anemia and haemophilia and so forth. In histopathology, we're training our graduates to conduct assessments on tissue biopsies, of course, and this is right from the initial processing and section cutting of tissue biopsies right through to the staining and imaging of these materials. While in microbiology, our students will learn all about the laboratory diagnosis of infectious diseases caused by bacteria, fungi, parasites, and of course viruses such as SARS-CoV-2. So typically our students will undertake these studies in the major streams over their final 3 semesters of study. We also have, for want of a better term, I guess, some minor areas of study, but they're not really minor in terms of importance, just minor in terms of the number of units, and that is the immunology and molecular biology streams. Studies in immunology, of course, are important for training our students to understand the mechanisms of infection and the body's response to infection. While molecular biology is, of course, the basis for the techniques used to perform the diagnostic tests for SARS-CoV-2 that I just described, but also for the diagnosis of all sorts of other diseases. So hopefully you can see how these disciplines fit together in helping to fight against this current pandemic. But the scientists are already busy working in these areas, okay, helping us to diagnose and to treat other infectious diseases and chronic diseases like cancer, diabetes, and cardiovascular disease. So the medical laboratory is a very, very busy place and has been incredibly busy over the past 18 months or so with the added work involved in dealing with the COVID-19 pandemic. What we see on screen here is Deepa again, one of our students that's on placement. And here she's actually receiving some instruction on a clinical biochemistry analyzer from, surprise, surprise, another one of our previous graduates. Next slide then, Donna. So whether a student is studying a Bachelor of Laboratory Medicine, as Deepa here is, or is studying a master's degree, the professional placement will see them being placed in a real working diagnostic pathology lab for the whole of their final semester. Here they'll experience laboratory operations in departments such as the specimen reception area, which is a key central area for the laboratory, within the clinical biochemistry labs, within hematology and transfusion, as well as microbiology and histopathology. So they will experience the whole industry, from the initial collection of biological specimens through to the various processing stages and to analysis and the final reporting of the patient results. Here they'll be expected to contribute to the laboratory workflow to an extent, but also to demonstrate the skills and the knowledge that they've developed during their training in the previous semesters of study. Now, while this is primarily a time for Deepa to finalise her training, this exposure in the laboratories is a great chance for her to audition, if you like, for a prospective employer. Now, there are no guarantees, of course, but it is not out of the ordinary for our students to secure work with host laboratories at the end of their placements. So while Deepa is almost at the end of her university studies, in the last few weeks, I've actually been taking in this year's first year students and teaching them basic laboratory skills. And these are techniques that they'll take right from this first semester of their study all the way through into the workplace when they graduate. So these students, for the most part, have never been inside a medical laboratory, and they've never undertaken the type of procedures that we teach even in this introductory first semester. So it truly is a training from the ground up, and that's the approach that we take with both the bachelor but also the master's students. We teach them the basics where they need them from the beginning, regardless of what their experience may be, and we take them all the way through to the advanced knowledge and skills that they are taught in the professional streams. The skills we teach are advanced skills suitable for working in human diagnostic pathology labs, but they are also the types of skills that are useful in other laboratory environments, of course. So for example, in veterinary laboratories, but also in research and development departments as part of pharmaceutical companies and in diagnostic companies. In addition, our students or our graduates also have great skills and great knowledge that they can put into practice if they wish to pursue a research career after graduation. Finally, of course, if studying medicine is an aim, you can use our courses as an entry into medicine as well. That's all, I think, Donna.
Thank you so much for that very detailed information regarding COVID-19 and our students' role and the university's role when it comes to the medical sciences during the pandemic. So while waiting for some questions from our attendees, we've got some FAQs in here that we have prepared that are of interest. So we can start with the first question, which is how much time is spent in the labs completing hands-on work?
So I guess if you think about this in terms of the initial course that we do, our course is very practical. If you're a person that loves to get into the lab and get your hands dirty, so to speak, although you'll be wearing gloves, this is a great course for that kind of student. What this means is in most units, particularly as you move into the second year and onwards, where you're in those professional streams, for many units, you'll have laboratory sessions for most weeks of the semester. So a lot of time spent in the laboratory learning the techniques that you need to know.
Thank you. Another question is, if I'm completing a portion of my study online because of border restrictions, when will I be able to complete lab work?
So while our course is very hands-on, as I just said, the early components can and have been taught in that online environment over the past year. However, our plan for any students that are affected by border restrictions like that are able to, will be that once they are able to come onto campus, we will look to conduct intensive practical sessions, which will enable those students to catch up on essentially what they've not been able to complete while they were based somewhere else.
Thank you. So, and another follow-up with that, how much time will I get to spend working in real labs with actual medical scientists?
So this is, I guess, a bit of a two-part answer. So during your study on campus, you'll be working in laboratories, learning those core skills and techniques, and you'll be learning them from experienced scientists that have worked in pathology labs and in research laboratories, and pretty much, you know, all your practical component will be taught in that way by experienced scientists. The second part, I guess, of the answer is following that on-campus study, you move into the professional placement period, and you'll spend essentially a semester working in private or public diagnostic pathology labs. And here, those students will be then mentored by experienced laboratory scientists. And they'll be ensuring that they cover all those key lab competencies that they need to graduate as a medical scientist.
Thank you. I guess you have answered the fourth question in your presentation a while back, but it says, can you provide more information? Will I get employment in TAS when I graduate from this course?
So, yeah, I guess there was a bit of a hint of that answer. We do have a great working relationship with the pathology labs in Tasmania. We've been working alongside them to train the next generation of medical scientists for many years now. They know our product, if you like, our graduates, they rate them really highly. And as such, a good proportion of our graduates are able to gain employment in Tasmania after they graduate. There's obviously no guarantee there, but there is certainly a definite possibility. We also have an expanding network of laboratories that we work with in New South Wales and to an extent into Victoria and the Northern Territory, who also appreciate the quality training that our graduates are receiving. So our students do have also the advantage of being from an AIMS accredited course, which holds them in really good stead.
Thank you. Okay, the last question from this page slide is, we do offer the Bachelor of Laboratory Medicine and the Master of Laboratory Medicine. Would you be able to explain the difference between the two?
Absolutely. So the bachelor program is, of course, a 3.5-year course, and it includes foundational studies, which lead into those professional streams, which I talked about. The master's course is a 2-year program that takes students straight into those professional streams. So if a student has already completed an undergraduate degree in science or in health, then that's a great entry point into our master's course. And it enables them to then gain a qualification that is accredited by AIMS, which is a really widely recognised organisation. And in addition, you know, either of those courses can be used, as I mentioned, as a pathway into medicine as well.
Okay. Thank you. A follow-up on that from one of our agents, his name is Sajias. I guess everyone is aware that both courses, Bachelor of Laboratory Medicine and Master of Laboratory Medicine, are quota course. And Sajid is interested to find out how many international students you can enroll for Masters and Bachelors separately.
How many do we accept into the course?
Yes.
We do have a quota, and I think it's about 16 per year, I think is, correct me if I'm wrong there, people.
Yes. Thank you. Okay, so we've got another slide for questions. And now this is about more of the degree itself and the graduate outcome. So where can I work with the qualifications from this degree?
Yeah, absolutely. I mean, this degree, of course, provides our students with the training to work in diagnostic pathology labs. Importantly, being AIMS accredited, it means that they don't need to seek further qualifications or training to work immediately in a diagnostic pathology lab. So as soon as they graduate, they're able to be employed in those types of labs. And it's important that, you know, not all courses are accredited. So that's an important note. We do have graduates that work in labs all around the world, as I've mentioned. While I guess the traditional pathway is for our graduates to work in routine human diagnostics, our graduates can find themselves working in other laboratories that require people with just really great lab skills, basically. So as I mentioned, this could be a veterinary laboratory, or it could be working for diagnostics or pharmaceutical companies working in research, or they may be able to branch into other areas in terms of you know, pursuing their own medical research or working in health management and things like that.
Thank you. I guess you answered the second question on this slide about our students working all around the globe. So, so they're qualified, their qualifications are recognized globally. Is that correct?
Is this peak professional body that represents recognized organisations? So that our degree being AIMS accredited means that it's.
Are you there, Jeff? You're breaking up a little bit.
Am I? I did get a message there saying my internet connection was unstable. So apologise, guys.
That's better now. So we missed that answer. Would you be able to repeat what you mentioned regarding the qualifications?
About AIMS, yeah. So the beauty of being an AIMS accredited course is that AIMS is really well regarded and recognised both through Australia but also globally. So being a graduate with from a course that is accredited with AIMS means that you will be recognised wherever you go.
Thank you very much. Now the question as well, that can I go into research with this degree?
You certainly can. As I mentioned at the start of my presentation, you can definitely pursue research if that is an interest for you. We offer both honours and PhD programs that the graduates of these courses can enter. So these are traditional entry points for research. I myself am a graduate of this course. Essentially, it was under a different name many years ago, but it's essentially the same program that I completed. And when I did complete that, I decided I wanted to pursue research. So I completed an honours degree and then finally entered into a PhD project within the school. Once I'd finished my PhD, I worked in various areas of research within Tasmania before I kind of finally found my way back to the School of Health Science and teaching in this same degree that I completed all those years ago. So there are honours and PhD projects available each year for interested students. And not this slide, but the previous slide was a picture of Brianna, who is a recent graduate of the Bachelor of Laboratory Medicine. And she's currently doing amazing work looking at antibiotic resistance in bacteria. And that's being done in our labs just down the hallway.
That's great to hear, Jeff. Okay, the last question from this slide is, you already mentioned it in your, at the end of your presentation that a graduate of this course can study medicine. So can you please explain this further?
So yeah, my understanding is completion of either of these courses will help you in your applications to apply for a position in the medicine programs.
That's great. Thank you very much. I guess there's only one question, but it's been slightly answered a while back from Pandawi. It's saying that when do you think that the border will be opened? If not, all students could study online. Laboratory is required during this course. So I guess our laboratory medicine courses are not offered online. Is that correct, Jeff?
So was there multiple questions there? Was it when the border is likely to open, was it?
Yeah, so we cannot answer that question just now.
We're hopeful that will be sometime this year. But yeah, in the meantime, we're able to certainly provide at least the first year of study in an online format. And then the aim is that those people that do undertake online study in that first year, when they do come on campus next year, for example, will be able to be caught up. So we'll run intensive prac sessions to make sure that they have all the skills that they need.
That's great. Thank you so much. There are no longer questions that's been received from our attendees. So I guess, we'd like to thank everyone for their participation. Thank you, Dr. Jeff Beckett, for the wonderful presentation provided tonight. We will be sending a link of these slides as well as the video presentation to everyone who attended. So, and if you have further questions later on, feel free to contact us. And the information of our contacts are on this slide. So you can call us, you can email us, or that's pretty much it about the medical sciences courses today at the University of Tasmania. So until then, thank you very much for all your time today, and especially to Dr. Jeff Beckett.
Thank you, Donna, and thank you everyone else for listening.
Bye.